Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video. All math-based, of course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Okay, step on inside, and if you are watching this in sequence with the times that I upload these, and that means you've been possibly following me in the Big Ideas Math Integrated Math 2 textbook journey, as we've been going through the first semester of chapters 1 through 4, where we've learned things on absolute values, exponentials and radicals, polynomials, specifically quadratics, graphing them, solving them, factoring them, distributing them, simplifying them, dealing with some complex numbers, things like that. 4 chapters of things, and now as we lean into end of semester talk, reviewing all these things together, I got about a 50, I think it's like a 50 problem set for you guys. A lot of graphics involved on them, and actually if you find it in the description section down below, I'll provide it right there. I'm not going to place it in my playlist for Big Ideas Math because it is not out of the textbook. That's specifically for things out of the textbook, but I will link that playlist for you if you want to find any of the sections that I have covered. I think there are only maybe 2 sections I haven't yet actually done at the recording, at the time of this recording, I should say. But I will provide this thing for you here. You have ample opportunity to print this thing out and fill in blanks within there. You don't need binder paper. You don't need your own graph paper. Now, this is from a colleague of mine, so I've not yet done the problems to tell you exactly what's there and what's not. I do believe when they have you solve, because I had to split the things apart to space them out, I do believe when you have to solve quadratics, they're forcing you to choose a method instead of saying choose your own method. I don't recall things on piecewise functions or inverses, excuse me, or exponential word problems. I'm trying to think of some of the things that I didn't see, but I haven't tried the problems yet. So we'll see how they look. We'll see what they do. This could take a while. I'll leave timestamps for all the problems down below as we work through it. And yeah, it might take some time because of some of the graphing. So just get ready for that, guys. I hope you enjoy what we put together, or at least that you learn from it, right? How much do we all enjoy math? And not everyone does here. Write your name, yada, yada. Let's go to number 1. For each function, describe the transformation and then graph the function. Indicate 5 points on your graph. Well, I'll indicate as many points as I can fit. That's my rule. And here's the thing. If you're watching from somewhere else and you haven't seen me do this stuff before, you might have to get into how I do some of my graphing because I never use a table. I go in relation to my vertex and based off of the function's behavior. That's it, and that's all. So absolute value of x plus 2, f of x equals that. Now, when it comes to the vertex form for this thing, we're looking at y equals a times absolute value of x minus h plus k. And compared to y equals absolute value of x itself, there's just a plus 2 on the outside like your plus k. That is a vertical translation up 2 units like that. This is where my vertex would sit as opposed to the origin. Everything else should be exactly the same as the parent function would be for a v-shape up 1 over 1 in both directions of the vertex kind of graph. Look, I already plotted 5 points. 6, 7, 8, 9, 20 points. Oh, look at all those points. So plotting all these points right here. I'm going to draw an arrow and such. You know what else is not on here that I didn't see it? We'll check, but I don't remember any domain and range questions. I can tell you right here, this domain is all real numbers, and the range, y is greater than or equal to 2. Oh, yes. So there's the graph. Now they want us to describe the transformation. You take what this would have been, and you shifted everything 2 units up, also known as a translation. We translate 2 units up. And that is my description for that one. Part B, y equals negative 2 times the absolute value of x plus 3. We're referring to the a value as negative 2, and inside this x minus h, you see this x plus 3. Instead of a minus, it's a plus because you're subtracting a negative, because I need to plug in a negative for x to make 0, one of the big things where you flip the inside part. That means this thing does translate 3 units to the left, like this. I'm talking about the 3 portion only. It's opposite of what you see in there. Plugging in negative 3 for x is what gets you 0 for y. It's what maximizes your values. And I say maximizes because this graph has a negative stretch factor, which means it flips over. So it's going to have an upside down V shape like that, and it will also be vertically stretched. Twice as large, twice as big. Instead of down 1 over 1, it's down 2 over 1, where I can plot a next point. Kind of treat it like a slope for these, in that you have a linear path that we can go. So, as far as describing transformations for this, we're going to be talking about the fact that it flipped over. We're going to use the word reflect for that. It's a reflection. We're going to bring up the fact that it vertically stretched. Everything is twice as tall as it was before. and that it shifted over to the left. Notice it didn't shift up or down. There's no plus k on the outside of this thing. So when it comes to this, we're going to say reflect over the x-axis. Excuse me, that is not well written. We reflect over the x-axis to flip that thing over. That's what the negative is doing. We vertically stretch this graph by a factor of 2. Not -2. The negative is what made this thing reflect. And we translated 3 units to the left. Okay. There's that absolute value graph. Part C. Y equals 1/2 times the absolute value of x plus 3 and plus 1. Now the plus 3 is the same as you saw before. Translate 3 units left, because when x is -3 is where this part becomes 0. Plus 1 is 1. That's where this thing comes up. 3 units left, 1 unit up. Vertex is at -3, 1. This graph is not flipped over. There's no negative with a, but a is 1/2. Last time it was 2. It made us double our things. Up 2 over 1. Treat it like a slope. You can also treat this like a slope. Now everything will be vertically compressed. Half the heights that they were before. Instead, you go up 1/2 to go over 1. But I'm not going to say that. I'm going to say you go up 1 to go over 2. It's going to make it a lot easier to work this thing out. Up 1 over 2, yada, 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 yada. No tables. No tables, please. So this absolute value graph upward in that fashion, starting from -3, 1. Every point's in relation to the vertex that I had there. So this is... we vertically compress this graph. Also, another word is vertically shrink. We vertically compress by a factor of 1/2. You could argue that because you use the word compress, you might say by a factor of 2. And I understand that. It's like saying divide by 2. I think using the word compress is just a courtesy for the fact that 1/2 is the stretch factor. Compression factor, if you will. We're also translating 3 units left and 1 unit up. 3 units left and 1 unit up. Should probably use the number 1. 1 unit up. Okay. Part D. Y equals -3x squared plus 5. Now, this is not an absolute value graph. I'm trying to move myself. This is not an absolute value graph. This is a quadratic function. You can treat this one of 3 ways when it comes to observing and seeing this graph and not using a table. It's all about plotting that vertex and going from there. You can think of it like vertex form the same way that we had our absolute value graphs. I can think of this as x minus 0 that's being squared. That way we know the vertex is at 0, 5. That's fine. We can also see that there's no b term. If you're used to having your vertex x value at -b over 2a, the b is 0, which means we're doing 0 over -6, which is 0 for x. Plug in 0 into here, you get 5 for y. So, I don't know, but 0 is the x value. It leads you to that vertex. Or that's literally just what you do. When there's no b value, the only translations you can have are vertical, nothing horizontal. This thing is going to take a -3x squared graph that's flipped over and stretched, and it's going to translate it up 5 units. Again, there is no horizontal translation. So my vertex is at 0, 5. This is not an absolute value graph, so it does not have absolute value behavior. This is quadratic behavior. When you go over, you go up a squared amount. Over 1, up 1 squared. Over 2, up 2 squared, which is 4. Over 3, up 9, having been 3 squared. But we flip this over, so we're going to go down instead of up. 1, 1, 2, 4, 3, 9, and we are going to triple those heights. This is a vertical stretch. Everything is 3 times larger. Not over 1 down 1, but over 1 down 3. Like an absolute value function, however, squaring a number does make it positive, so this will also be symmetrical. Of course, we're going to make them negative after that. Instead of over 2 down 4, I'm going over 2 down 12. These are some other points I have. Without needing to use a table, there's the behavior that this quadratic U-shape function that looks like a parabola will have. And here is the graph. Sometimes you'll hear me call them 8-second graphs. That didn't take me 8 seconds to graph because I had to describe it. But we reflect it over the x-axis. We vertically stretched by a factor of 3. And we translated 5 units up. Now, I believe we're going to have a lot of quadratic function things to do because there are so many sections for which we did it, and there's a whole chapter in which we did it. Absolute values was only one section, so to have 3 problems there was actually pretty nifty to be able to use those. I don't know how many times we get more absolute value ones to do, unless maybe we get to write equations, or I don't know, something else. We'll see. But translate 5 units up. Hopefully you notice the order that I'm writing these descriptions as well. I'm writing the A things first, the H and K's next. I'm just going in order, not only left to right, but also alphabetical. A comes before H, which comes before K. You have to stretch and reflect before you mention translations, even though when I graph, I do the translations first. That's because I'm aware that I'm doing everything in relation to my vertex. I'm not treating my vertex as 0, 5. I'm treating it as an origin. That when I go 1 over and 3 down, it's almost like 1, negative 3. It's not really. It's really 1, 2. But that's the point, is that's how I'm treating it. Part E, lastly, at least for this question set, we have y equals negative x minus 3 quantity squared plus 4. If it wasn't made obvious from the last thing that I wrote, there is a vertex form for quadratic equations as well, which includes a, h, and k, only it's now a quadratic function. So our vertex is at 3, 4. If I plug in 3 for x, I get 4 for y, and this will be a maximum point because this graph will flip over. This is a vertical, it's not a stretch really, but it's a vertical stretch factor of negative 1, which means graphs flipped over, and we go 1, 1, 2, 4, 3 squared is 9, 4 squared is 16, which I can't fit, no, I can't fit totally. It's probably further down here at negative 12, but I can get that concept. And we reflect it on the other side of this invisible axis of symmetry, something of which I'm probably going to be drawing in future problems when I feel like it's more needed. So there is this parabola here. And again, I'm always going to plot as many points as I can fit. The instruction on here said fit 5 points. Plot, indicate 5 points. I'm going to use that. So we reflect it over the x-axis. I probably got to change this tip right here. I kind of feel a scratch. It's a little uncomfortable. Reflect over the x-axis for one thing. And then we translate 3 units right and 4 units up. Hopefully I can find that pen placement like I said. And 4 units up. I may pause this at some point to fix this tip. It's it's having some problems. Okay, so there is number 1, parts A through E. Let's move forward. Now, like I said, a lot of graphing begins this thing. Okay. Number 2, graph each function, indicate 5 points or more. Include vertex, axis of symmetry, and y-intercept. These questions are different when it comes to, and actually, let me check and see what's factor. Some of these look factorable, so let me see what kind of has moving forward. Okay, this one's factored, but it says solve by graphing different kind of question. Okay, these questions are not in vertex form. Now, there's a way of getting problems in vertex form. There's actually more than one way. I can think of 3 of them. To do pretty well, and I got to mix and match how I'm going to go ahead and do that. Actually, there are probably 2 ways to do it in some problems, and 3 in some others, depending on whether or not it's factorable, because this is not factorable. One method of getting your vertex I mentioned before, this is ax squared plus bx plus c. Your vertex x value is at negative b over 2a, like that. When you plug in negative b over 2a into your equation, you get the y value of the vertex as well. This is where the vertex appears or occurs. So this is, a is 2. A is 2. So this is negative 4 over 4, which is negative 1. The x value is negative 1. And f of negative 1, if I substitute negative 1 into here to get the y value, I get negative 1 squared, which is 1 times 2 is 2. Plus 4 times negative 1, which is 2 minus 4, which is negative 2, plus 1 is negative 1. So you plug in negative 1 for x, you get negative 1 for y. Your vertex is at negative 1, negative 1. This is one way we can do these problems. It's the only way I'll do this one. It's probably the way I would have preferred. Now, they didn't ask you to write this in vertex form, but if I were going to, this would be, because I don't know if they're going to ask later, this would be my h and my k, and my a value would have been 2. So here's my a times x minus h quantity squared plus k. This would have been the vertex form of that graph. So if you're used to graphing out a vertex form, here's what we'll do. But of course, we already found the vertex for that. So We have our vertex at -1, -1. Our vertical stretch factor is 2. And we're going to, let me do this time. They do say include axis of symmetry. So I'm going to go ahead and draw one of those right here. It's the vertical line that goes through here that's at x equals 1. Give me a second. An axis of symmetry at x equals 1, -1. And then that's where I can talk about that reflection more. When I go over 1, I go up 2 instead of 1. When I go over 2, I go up 8 instead of 4. I'm doubling that amount. 6, 7, 8. And these points reflect across this axis of symmetry. 1 away, 2 away, like that. You get those points. That time I only did plot 5 points. Now let's see what else that they want on here. It's in standard form, so we can talk about y-intercept. And we can talk about, I think that would kind of be it. Include vertex, okay. Axis of symmetry and y-intercept. I don't know if that meant on the graph itself, but the y-intercept is this guy at 0, 1. Or just 1. Sometimes people just say 1, that's fine, either or. And that y-intercept is also indicated right here. It's the constant value, the value of y when x equals 0. That is number 2, part A. Number 2, part B. Notice they didn't say describe transformation, so I'm not doing that. Number 2, part B. I'm going to go about it a different way. I could use the -b/2a if I wanted to. There's no problem with that. But let me show you a different method that can be used in the future. This one is factorable. This factors into x plus 5 times x plus 1. What I get out of factored form is the unseen stretch factor of 1, that's fine, but what I get out of factored form is a product. If I set that product equal to 0, y, if y equals 0, then the x's that I can find here will be my x-intercepts. And when it's factored, that's very easy to find. If x plus 5 equals 0, then x equals -5. And if x plus 1 equals 0, then x equals -1. These are my x-intercepts. -5 and -1. Those are 2 points on the graph. They are not the vertex, but they are 2 points on the graph. And they are not the vertex, but I can find the vertex with this. If I want to find the vertex, the x value of the vertex will be exactly halfway in between these 2 points, because these are 2 corresponding points in a parabola. Probably haven't mentioned this, but I've kind of shown it. Parabolas are symmetric all the time. They have that axis of symmetry. And the axis of symmetry here is the halfway distance between -5 and -1, which is -3. How do you determine that axis of symmetry? You can count it, half that distance, right? They're 4 apart, so 2 away from 4 is -3 on here. You could also calculate it by averaging your 2 values here. Your axis of symmetry is at x equals -5 plus -1 divided by 2. Average your values and divide it by 2. That's the vertex x value. And again, axis of symmetry. The y value of the vertex still needs to be found. You have to substitute -3 in for y. So y equals -3 squared, which is 9, plus 6 times -3, -18. 9 minus 18 is -9, plus 5 is -4. So y equals -4. Your vertex is at -3, -4. So -4 on the axis of symmetry right here. Now they did say include the y-intercept. So the y-intercept is 5. When x is 0, y is 5. So there's this point. And I can also reflect this across 3 away, 3 away. If I wanted to graph it right now, I could. I have 5 points. They represent that which make my parabola. I'm going to include one more set of points and confirm all this work though. With that stretch factor of 1, I get 1, 1, and reflect 2, 4, reflect 3, 9, and reflect. Those are already on there. So I got 7 points for you guys here. Now, I just noticed, although I didn't mention, that when I found my vertex y value, I substituted them in the standard form equation. I generally don't do that if I have the factored form. I should have substituted -3 into here. -3 plus 5 is 2. -3 plus 1 is -2. 2 times -2 is -4, so you still get the same y value. Just whichever one's easier or faster for you, mental, what have you. You can use either. I'm just saying that normally I do it at a factored form if I have factored form. So I didn't use -b/2a to get -3 for x this time. I just showed you a factored form version, which now I said there are different ways you can get your vertex. Those were 2 of those ways. A third way, I'll show at some point if it shows up, it's using something called completing the square. So you can do that and get in vertex form as well, depending on if they pop up. I sure hope they do. Graph each function, indicate x-intercept. Oh, I didn't write. Hold on a second. Let's look at this. Vertex, axis symmetry, y-intercept. Y-intercept, this time I'm just going to put it as y equals 5. Okay, I think that's all of it. All right, number 3, part A. Indicate x-intercepts, axis symmetry, y. Okay, so all the same stuff as before. No new instruction. Now, this does have a factorization. If I take out -2, I'd have x squared plus 5x plus 6. The question is, can I use factored form to get the rest of the stuff in here? And I'd say yes. This set factors into x plus 3 times x plus 2. You can choose to use this or -b over 2a, either or. But this does mean you have x-intercepts of -3 and -2. I probably shouldn't be saying x equals for these. Those are the solutions when you set equal to 0. -3 and -2 being the opposite of those when you set them equal to 0. So x-intercepts -3 and -2 are here. The axis of symmetry this time is halfway in between, which is a little wonkier because it is a decimal. It is -2.5. When you average -3 and -2, -2.5 is what you get. So it would be this guy, axis of symmetry, at x equals -2.5. And that is an x equals equation. You do need the x for this one. This time I'm going to use this equation and substitute -2.5 for x. -2.5 plus 3 is positive 1/2, or 0.5. -2.5 plus 2 is -1/2. Negative times negative is a positive. 2 times 1/2 is 1 times 1/2 is 1/2. So y is 0.5 or 1/2. I'm writing it like this. Sometimes I write it like a fraction, but the vertex is -2.5 comma 0.5, like that. So it's going to be right here. It makes sense that the graph goes downward with the stretch factor of -2, whether I use standard form or this guy right here. The y-intercept is at -12. It would be out of reach, but I'll plot close to it just to get the idea that it would be kind of there. Because the problem with this graph, when it comes to my tableless method, is that when I'm going to go over and off from the vertex is at decimal values for both x and y. So when I say I go over 1 and down 2, given that stretch, I'm going to hit right here. So if you're more of a fan of actually plugging in integer values, go ahead and do so. Just make sure you know you build around -2.5. So -3 and -2 are the same distance away. -1 and -4 are the same distance away. You can plug those in. In fact, at -12, I'm 2.5 away here, so 2.5 away should be -5, -12. So that's one of the points I should have. So let's keep going. Over 1, down 2. Over 2, I should be able to go down 8. Down 8 right here, like that, because we're doubling 4. And so I think that's going to be enough points that I can fit. I think I've had enough. And there is my downward curve on this guy. Right there, hitting the y-intercept as well. Y-intercept of -12. Indicate, oh, it says indicate x-intercepts, axis of symmetry, and y-intercepts. I did not see that instruction separately. My x-intercepts, and maybe this is where they wanted you to factor. Shoot, I should have probably looked at that. X-intercepts are -3 and -2. Oh, I already wrote that. Axis of symmetry, okay, I think I got it. I didn't need to write the vertex this time, apparently. Part B is also factorable, and because they're asking for x-intercepts, I guess that's really what we're looking for and looking to do. I have a greatest common factor of 3x, and if I factor that out, I'm left with x minus 2 on the inside. This is a factorization as well. It's a product, and I might want to write the x around parentheses to stress the fact that 3 is my a value, it's a stretch factor, and x is one of the factors that leads to an x-intercept. When I talk about x-intercepts, setting y equal to 0, if x equaled 0, I would get 0 out for y. So 0 is one of my x-intercepts, and 2 is the other one right here. So I get 0 and 2 is my x-intercepts, and averaging 0 and 2, you get 1. That is the axis of symmetry. X equals 1 right in between here. So I have an axis of symmetry. Let me move my face again. axis of symmetry at x equals 1. Substitute 1 into this equation. 1 times negative 1, I get 3 times 1 times negative 1, I get negative 3. So I got a vertex at 1, negative 3. That's right here. And they ask for the y-intercept. It's also if an x-intercept is 0, then your y-intercept is also 0. It has to be. That's either the y. You can only cross the y-axis once in a function. They are functions after all. And also, the constant is missing. That's because there's a 0 that's added with it. That is your y-intercept there. So I should add another point if I can fit it. Over 1 up 3 seems to agree with this vertical stretch factor. If I go over 2, I should be going up 12. So negative 3 plus 12 is 9. So I should be over here. And 2 away, I should be over there as well. So I have my axis of symmetry, x-intercept, x-intercepts, y-intercept, and vertex. Those 4 and 5 points plotted on the graph as well. And there we go. All right, numbers 4a and 4b. Is that natural log of y? What are we? Oh, that says in. In y equals. Oh, we're writing equations. Got it. Let me move myself. Forget what I said about natural logs. You won't learn that until next year. I thought it said ln. Okay, we're going to write the equations for these in vertex form for both of these. Now, there's more than one way to do this. It's the same approach. One is more mental, one's more hands-on. And I'll do the hands-on one and talk about the mental version with it as well. Y equals a times x minus h plus k form. What we need are the vertex and vertical stretch factor, basically, right? So your vertex is your hk. We're talking about this guy right here. So for all intents and purposes, the equation for now can look like y equals a times x minus this h and plus this k. But we need the a value. The more hands-on version of this is taking an xy value that is on this graph. You have these two that are known for sure. You can use either of these two. You'll get the same answer because the way absolute values function. I'm going to choose 6, 0. Actually, I'll choose 0, 0 just to hit home a point about how this works either way. 0 for y and 0 for x, and we'll use that to solve for a. Then we'll insert the a into here. So 0 equals a times 0 minus 3. Plus 2, absolute value of 0 minus 3. That's the important part. Absolute value of negative 3 is multiplying with a. Let's do 2 steps in 1 here. I'm going to subtract 2 from both sides like that, and I'm going to take the absolute value of negative 3. The absolute value of negative 3 is 3, which is multiplying by that a, and we divide both sides by 3, and we get a equals negative 2/3. Therefore, this answer is going to be y equals negative 2/3 times the absolute value of x minus 3 plus 2. A lot of people tend to ask, you bring the x and y back? Well, yeah, we temporarily inserted a solution. There's an infinite number of solutions on here. We temporarily inserted a solution into here that worked in conjunction with this vertex to say, what's the one stretch factor that would make this work? And it's negative 2/3. Now, does negative 2/3 make sense for this answer? It does. Like I said, from the vertex, we can treat our graphs like a slope. The fact that it goes down means it will be negative. We're going down 2 and over 3, down 2 and over 3 to make this happen. So treating it like a slope instead of up 1 over 1 and a stretch factor of 1, this is down 2 over 3. It's a stretch factor of negative 2/3. This is a vertical compression by a factor of 2/3. That is the mental way of getting that exact same thing for absolute value graphs, but that is the answer. Okay, that is number 4. Let's go to number 5. Let's move my face. This is going to be a quadratic, and we're going to apply a very similar principle. Now, my mental approach might not work very beautifully with this. It can work. You just got to know what I would do with it. Let me talk about that first, and then I'll go to the other method. The same thing begins as how we would do before. We're going to write this in vertex form by identifying the vertex first. I got an h of negative 3 and a k of negative 4. So my equation would be y equals a times x minus negative 3, or x plus 3 quantity squared, minus 4. That's the beginning portion. Now we got to find a. And here's what I'm going to do. I'm going to choose the point that they gave us, despite the fact that there are better points to use, but I'll show you that this works no matter which points I use. So I'm going to use this point that they gave us and talk about this. I won't call it a rise over run, but when I'm going over a certain amount, how much am I going up? And how much is it in comparison to what I would normally do? When I'm going over 3, I'm going up from negative 4 to 1/2. So I'm going up 4.5. you can write this part physically or you can think about it mentally. Normally when I go over 3, I would go up 9. I'd go up 3 squared. So if I'm taking 9, how much I would go up, and I'm multiplying it by my vertical stretch factor A, and now I'm only going up 4.5, what is A? Let's divide both sides by 9. 4.5 divided by 9 is also 1/2. That's the A value. I did that without the substitution of that for X and Y, for X and Y. Now, there are other points that are on this graph. They gave us this one. Okay, that's fine. There's this point as well, which is, it's 1,4, but I don't care what that is. I care how much I go over and up. When I go over 4, I'm going up 8. Well, normally I'd go up 16, right? 4 squared. Well, 16 times A is 8. Divide by 16 from both sides. A is still 1/2. You still get the 1/2. That's my point, is that you get the 1/2 no matter what you do, as long as it's a point that's on that graph with respect to that vertex. So using the other method, of course, what I could have done instead was chosen this 0 and 0.5 as my xy. So taken this same equation and done 0.5 for y equals A times 0 plus 3 squared minus 4. Let's add 4 to both sides right now and get 4.5 equals A times 0 plus 3 is 3, and 3 squared is 9. A times 9. That looks just like what we were doing right here, right? I don't know which one's more steps or less steps for you. My concept is basically with my tableless method saying, if I were to graph this, what equation would have it been? I'm going over 4, going up 8. That's half of 16. Well, A is 1/2. So the final equation is going to be y equals 1/2 times x plus 3 quantity squared minus 4. Okay. All right. Let's graph exponential functions. This is out of chapter 1 stuff from the Big Ideas Math textbook. Now, the Big Ideas Math textbook doesn't do as many things in the form of, doesn't use as many A values. This form is y equals A times b to the x power. But I believe that the book really sticks to just y equals b to the x power. So that's unfortunate. There's not really an A involved, but you know, A tends to represent the y. It's a vertical stretch, but for our sake, it kind of also represents the y-intercept. When x is 0, see, anything to the 0 power is 1. So when x is 0, you get a y value of 1, but times that A would be A. Times 2 is 2, times 5 is 5, times -7 is -7. So it represents how much you stretch at that time. B represents your exponential growth or decay factor. Exponential growth or decay factor. Every time x increases by 1, there's another b that's multiplied in this problem, because that's how exponents work. The exponent describes how many b's you're multiplying with each other. So when x is 1, there's 1 b multiplied. When x is 2, it's 2 b's multiplied on top of themselves. Determine if it represents growth or decay is also based on whether b is less than 1 or greater than 1. And by less than 1, I don't mean negative and 0. I mean between 0 and 1, like a fraction like this. This b, this y equals b to the x, represents exponential decay. It's positive exponential decay because a, of course, is just that positive 1. Now, again, when I plug in 0 for x, I get 1 for y. 1/2 to the first power, 1/2 to the 0 power is 1. That would be 1. But every time x increases by 1, I'm going to be half the height that I was before. Every time when I increase x by 1, I'm going to be at 1/2. Times another 1/2 is 1/4. Times another quarter is 1/8. And 1/16, etc. And it keeps getting closer and closer to 0, technically never hits. Now, if I'm multiplying by 1/2 every time x increases by 1, that means every time x decreases by 1, you're dividing by 1/2, which also means multiplying by 2. And that makes sense. If I did 1/2 to the negative first power, that means I can turn the negative 1 positive. I can flip this fraction. It becomes 2 over 1 to the first power, which is 2. So this will be a 2 here. Or half of 2 is 1, right? Go backwards. You double going this way. So 4, 8, 16. You know what? I should do this. Let's do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I can do this for the next problem as well. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, 16 is, there we go, 10, 16 right there. And the next one would have been 32, which is not quite there to fit. So I'm going to just plot what I can fit here. Now, something. Forgot what I was going to say. Oh, I'm also slightly realizing, listen, this final is not as this review is not as comprehensive as can absolutely be, and that I don't know if there are exponential and radical things all around, doing things like negative exponents and stuff like that. That's a lot of chapter 1 material. So this isn't everything. This is a lot of quadratic stuff, and some of these are in the way, exponentials and things like that. There's that. Did I need anything else? Determine growth or decay, and that's it. So there's the graph, and this is exponential decay. The points get closer to 0. There's one more thing I'm going to plot, and it's this thing right here. I'm going to draw the asymptote. That's really the, if I'm going to hit this thing home and talk about, we never actually touch or cross 0. So that asymptote's that reminder of that. This dotted line right here, horizontal dotted line that says, you shall not pass, you shall not touch. Okay. All of these will have that because there are no vertical translations. Excuse me. All exponential functions have it, but all of them will have it on the x-axis because there are no vertical translations of this guy. So it's going to stay like that for this next problem, which I'll do in green. In the second question, we have y equals 3 to the x power. Again, your a value is just 1. So 3 to the 0 is 1. We're going to be able to start right there. No stretch. Now every time x increases by 1, we get to multiply this by 3. This is exponential growth this time. Oh, I didn't bring these things over. Give me 1 second. So this is positive exponential growth because you see this thing take off in that direction like so. If the graph was negative, it could also grow negatively, but I don't believe we're going to be dealing with the negative graphs in this format here. So I have this. I have this happening. Times 3 is 9. Times 3 would be 27. 5, 10, 15, 20, 25. 27 would be about right there if you really wanted to fit something. That's a little closer than 32. And I'd be dividing by 3 going to the left. So I'd get 1/3. A third of a third is 1/9. And 1 over 27, forget about it. So if I were to try and reach for the sky here and actually get both of those points involved, even that one way up there, I would try my best to. Nope. I would try my best to. Yeah, that was pretty good. That was a good straight shot. Oh, I messed up right there. I'll erase that part later. Hold on. And then let's be a little more precise. Cut through. There we go. Like I said, on the blue one, I had no other perceivable point to get closer and closer to, so I just kind of ignored it. But there's that one. Got to draw an arrow at the top. And this is exponential growth. Okay, a lot of graphing so far, but there is that graph. Looks beautiful. Okay, number 6, solve each function by graphing. We're getting back to some quadratics here. Solving by graphing, now this is already in factored form, so I get to kind of use, so far I've only used negative b over 2a, I think once, maybe twice on the earlier problems. But solving by graphing here in factored form, listen, this is kind of a weird question because the solutions that I get here, oh gosh, how do I say this? When solving by graphing, the goal is to take an equation, make it say like y equals something, whatever, and draw its graph and seek where it hits the x-axis, say there and there, and boom, you get them. But the weird part is here is not only is it already factored, I mean, that's the big part, that when it's factored, I can solve out of factored form, which means using zero product property, I would get these points right here, and those are the solutions. I'm trying to find what x values give me 0 for y, or what x value makes this equation true. 3 would make this turn into 0, and -1 would make this turn into 0. But it's almost like I don't have to graph afterward because I solved algebraically, incidentally, getting those answers. Let's do the rest of the graph, but those are the answers right there. Okay, so it's a little backwards to go forwards. If I literally went backwards to go forwards, I would actually distribute this, and I would find the vertex using, say, negative b over 2a, something like that. Maybe I should do that, but this was set up like this. I can't really close my eyes and pretend like it's not there. Anyway, if I want to graph and get the rest of this, we can do that vertex stuff again, get the axis of symmetry as x equals 1. It's right in between those two right there. Substitute 1 in for x into a y equals version of this equation. 1 minus 3 is -2. 1 plus 1 is +2, and you get -4. Stretch factor is 1, so I can go 1, 1, 2, 4. Oh, I found my answers. 3, 9. like that, and you get a quadratic that is going like that. But the solutions are the x-intercepts, x-intercepts specifically because I'm using that method where when it's set equal to 0, those x-intercepts end up being the answers. Okay. Now, part B has a different premise, and I'm going to treat part B as it is right now. A second version of this method is to graph it as if you have two different equations, y equals this side and y equals that side. I'm going to write it as negative 2x minus 1. We graph them separately on here, and we find where they intersect, if at all. They may not. But we find where they intersect, and where they intersect are the solutions to this thing. You could alternatively set this equal to 0. Without solving by factoring, I just mean use your negative b over 2a thing, or rewrite it in vertex form. You have a lot of options from there if you wanted to do something like that, which is, I still haven't done vertex form out of completing the square, but I'll do it if it shows up. Right here, y equals x squared. This is the parent function that's as basic as 1 squared is 1, 2 squared is 4 from the origin. Definitely not using a table here as long as you know your squares. But there is this quadratic. You really need to draw this best as possible because this is where you're going to draw another line with this, and you need to stingily see where it's intersecting with this graph because it might be very stingy indeed. Okay, doing my best there. Y equals negative 2x minus 1 is a slope-intercept form equation, y equals mx plus b. So I start from my y-intercept of negative 1, and I can go down to right 1 to get points here, and also up to left 1. And this is where, like I said, it's stingy. Boom, I actually hit that point, but I hit this point here that's not on green anymore. So it looks like this is tangentially intersecting with this graph. I mean, it's only kissing and touching at one point, and then it moves off. So it's going to look like this right here. Now, it's kind of hard to tell because my graph probably isn't perfect with this, but it's only intersecting once. It crosses here at negative 1 comma negative 1. The y doesn't matter for these particular problems because y was not involved. I'm asking what x value makes the left side equal the right side. That x value is negative 1. There's only one answer this time. Like I said, there's more than one way we can do a problem like that, but that's kind of the ability that I went with for there. Solve by graphing. Let's see if there's more than that. This is solving systems by graphing. This is where our answers will actually be ordered pairs this time, so I get to do more of the same. And score, I get to actually also talk about what I wanted to mention before, which is the negative b over 2a stuff. Let's take this topic. This is where you literally graph them as they are. You have no choice but to do that for the system because we have to find the y values that make the ordered, x, y. I need my ordered pairs right here. So with this one, I'm going to take this equation and I'm going to write x squared plus 2x plus 5, but I'm going to split off the 5 over here. I'm going to add in a different number that gives me a perfect square trinomial with these three terms, and I'm going to subtract that same value out because I can't just, without consequence, inconsequentially, add something to an equation without keeping any balance. Now, to complete the square, I take half of this number and square it. 2 divided by 2 is 1. And 1 squared, I'm going to write parentheses squared. 1 squared is 1. This is what I'm going to add in. And I'm also going to subtract out. This is a perfect square trinomial. This is x plus 1 quantity squared. That 1 is the one that goes inside there. 5 minus 1 is 4. So here's my vertex form. This is one version of writing that. So that's this one I'm going to do in blue. My vertex is at negative 1 comma 4. And I have a stretch factor of 1, as you kind of saw previously. 1, 1, 2, 4. It's kind of all I can fit here. So if they intersect, I'm going to go ahead and probably find it within there. But that's this graph. You could have used negative b over 2a and all that. Again, I said that there are 3 different methods we can do these. Only 2 if something's not factorable, which this one was not, or if completing the square doesn't feel like a good thing to do. So I don't want to do completing the square on this problem. I'll use negative b over 2a for this one. The other one is y equals negative 2x minus 5. So negative 5 is the y-intercept. I'm going to say I have a feeling they don't intersect, but they might. Down to right 1 going this direction and up to left 1 over here. I have a feeling these don't intersect. There we go. Okay. Now, as the parabola keeps increasing, as x keeps going left and right and such, then the parabola does keep increasing its sharpness, which means there's no chance that these will ever intersect. When we're talking about solving a system, we want to know what x's give us the same y's. Where do they intersect? They don't. There are no real solutions to this. There are imaginary solutions for which we're not seeking because we don't see where they cross on a graph, where they intersect, of real axes. All right, part B. I said I'd use negative b over 2a. I lied. I am going to factor this and go into vertex form. This factors to x plus 2 times x plus 1. I said vertex form. I meant factored form or intercept form. Your x-intercepts are negative 2 and negative 1. So I'm going to go ahead and plot those, negative 2 and negative 1, like so. The axis of symmetry is halfway in between at negative 1.5. And if I substitute negative 1.5 into here, I get negative 1.5 plus 2 times negative 1.5 plus 1, which is 0.5 times negative 0.5, or negative 0.25, negative 1/4. So my vertex for this one is at negative 1.5 comma negative 1/4, like that. Very, very small like that. I also have a y-intercept of 2, and I can reflect that over 1.5 way, 1.5 way, like that. I can also fit 1, 1, 2, 4, 3, 9, 9 up from my vertex, and I can plot the graph from there. So I got some distinct points in my intercepts, both the x's and the y-intercept. I got distinct points in going 1, 2, and 3 away from there. And this should be a pretty precise graph overall, except for just that one part. Okay. That's the top one. The bottom one, y equals negative x minus 3. Okay, these might not intersect again. So that, okay, so. I want to find ones that intersect. Again, I didn't make the problem, so we'll deal with what we have. So slope is negative 1. This is negative x minus 3. The slope is negative 1, like so. Down 1, right 1. Okay. I can promise you the graphs are accurate. Just narrowly misses. It doesn't actually hit. They just narrowly miss each other. So once again, like the last problem set, if they don't intersect, there are no real solutions. I'm hoping the next set actually will intersect when we do these, but we still got to sketch and complete this graph. If they don't intersect, we'd say no real solutions. Once more. Good stuff, right? All right. Part C, it's asterisked. I'm not quite sure why, but we got a quadratic graph and an absolute value graph. It's possible that it's asterisked because maybe you have to use a calculator. I'm not sure. I haven't done it before. So let's see. I'm going to do one in blue and one in green. The blue one has a vertex at negative 3, negative 4. And you have a stretch factor of 1. So I got 1, 1, 2, 4, 3, 9. I'll sketch that. And then, I'm going to do the absolute value graph after. So it looks like we do at least get to revisit absolute value graphs at least one more time here. So, okay, so this one, I think they'll intersect. So this one has a vertex of negative 3, 0 here, and a vertical stretch factor of negative 3. These are not U shapes, these are V shapes. So this is down 3 over 1. That's where it's going to intersect. Down 3 over 1. And down 3 over 1 in the other direction, like so. And this has graphs that do a little bit of that. And a little bit of that. And these are these are intersecting at these particular points here and here. Your solutions are not just x equals anymore. It's all about ordered pairs. These are negative 2, negative 3, and negative 4, negative 3. This is the first time we actually got to see ones that do intersect, though, with a system. And that's what they'll be there. That's part C. All right, number 8. We are graphing parts A and B. These are inequalities. Y is greater than negative x squared minus 2x plus 15. This is factorable. I haven't seen negative b over 2a in a while. I am seeing a bunch that are factorable. Whenever I can factor, I go for it. I'm sorry, I could also use completing the square, but it would be trickier with the negative. So I'm going to go ahead and do the factoring joint here, and I get factoring out a negative. This can factor into x plus 5 and x minus 3. So this helps me get intercepts of -5 and +3. I'm going to try and do a lot of this mentally, if that's okay, now that we've dealt with some of the stuff. Halfway in between -5 and +3, 4 away is -1. So I can plot x equals -1 as my axis of symmetry here, like that. If I plug -1 into my equation, or inequality, but treat it like an equation. We're trying to do y equals when x is -1. So the opposite of -1 plus 5, 4, times -1 minus 3, -4, is +16. That won't fit on this graph. I got to get a new set of graph axes for you. Give me 1 second. I should probably change that. Uh-oh. Let me pause this for a sec. I need to get graph axes for here. Okay, I'm back. Got it a lot bigger, right? So what this is now, I don't know if I can end up fitting this on the PDF because this fits specifically on a certain page at the bottom. So we'll see what we can do. But the point is, when I substitute -1 for x, I get 16. Whoops. I get 16. So my vertex is at -1, 16, which is up here. That's the only way I can fit that guy. Now, the other points were -5 and +3 based off these intercepts here. And I have a stretch of -1. So I can go 1, 1, 2, 4. And you know what? I should have noticed that. I had a y-intercept of 15. I should have noticed that it was going to be all the way up here. An axis of symmetry even. Hold on, let me get that. All right, so there's that. 1, 1, 2, 4, 3, 9. 3, 9 over 3 down 9 there. And 4, 16. Over 4 down 16 gets those other 2 points that are like that. I'm not solving this by graphing. I'm just graphing this inequality set. Over 5, I'd go down 25. That's 5 squared. So that's going to go all the way down here. And that's the last set that I can actually fit. Now, I would draw the curve through here. However, being a greater than, not greater than or equal to, means we're going to draw dotted lines for these because points on the curve should not count as solutions to this inequality, like so. Now, I'll be honest. I mentioned this chapters 1 through 4 stuff. I haven't covered this stuff with my students, graphing inequalities. So it's possible you haven't as well. If you're watching this video, I'm not sure. This would be out of something in chapter 3. I think it's 3.7. Maybe you have, maybe you haven't. I'm not sure. The greater than has to do with shading above this curve here. Now, I should probably actually continue this downward just to get the version of if I'm going down, down, down. Shading above here means everything on the outside because these are above, above, above the curve. So when I do this shading, this is a big boy curve now, but when I do this shading, it's going to be looking like this right here, all around and through and such. I don't know, this is going to take a little bit to do, so it's probably easier to box it out and then just erase the inside. I don't know, but this is as thick as I can make this curve thing, so I'm going to try my best just to kind of wrap around and do that for a little while. Hopefully you're okay with that. All these are solutions to this inequality. Any xy's that exist outside of the parabola of the curve will make a true statement for this thing. If I plugged in 5, 11, this would make a true statement into there. The y would be greater than whatever I'd plug in 5 for that. And there's the graph. All right, part B. This is a system of inequalities where we kind of have a similar concept, and who knows, I might have to change my graphing thing. I'm not sure. This time I'm going to just keep it at a standard form. This translation is just 4 units down, so I can go 4 units down like this, and I can go 1, 1, 2, 4, 3, 9, that kind of thing. The y-intercept is also the vertex, so I'm going to just do that. I don't really need a negative b over 2a. I don't need a factor, although if I did factor, I'd get x minus 2 times x plus 2, and that does seem to reveal exactly what we just found here, which is what? Which is the x-intercepts of -2 and +2. Now this also has that greater than thing, so it's not also equal to, which means dotted lines are going to be a thing in this. They're a portion of what we got, so I'll do a dotted line. And we are shading above this one as well. The difference is with this graph facing upward, this is going to be inside the parabola this time as we shade upward. That's going to be points that are above. So points above look like this set right in here. So here's the shading we get for the top inequality in the system. Oh man. Here's the problem. There's kind of overlap now when I do this. Sorry about that. Let's find a better way of doing that. It didn't skinny up this time. This is really hard to make happen. All right, but anyway, part B. I'll do part B right after this. Part B. Okay, as best as I'll do. Not part B, the second one. Negative x squared plus 3x plus 4. Okay. Factor out the negative. And this is factorable within here. I really haven't used a lot of negative b over 2a. This factors into x minus 4 times x plus 1. This ain't going to be a very pretty graph. The x-intercepts are positive 4 and negative 1. Let's use a different color. Let's use this purple. So positive 4 and negative 1. Halfway in between is 1, 2, 3, 4, 5. Halfway in between is at x equals negative 1.5. So vertex x value, or positive 1.5. And I plug 1.5 into here. I'll get y equals 1.5 minus 4 is negative 2.5. 1.5 plus 1 is positive 2.5. Negative times a negative is a positive, and I get 6.25, 6 1/4. So at 1.5, I go up 6 1/4 right here. And I'm going to try not to do dotted line stuff because, or excuse me, like an axis of symmetry, because I want just the graphs to speak for what I have here. Y-intercept is 4. That means there's a corresponding point that's another 1.5 away, 1.5 away, 3 away right there. I got 1, 1, 2, 4. Fit as many as I can here. 3, 9 down. That would be at, I think, right there. 4, 16. 1, 2, 3, 4. 16 down from that is, I think, right there. And this time when I draw this curve, because also equal to, I'm going to be drawing a solid line. Now, for a system of inequalities, unlike a system of equations, we are not, our goal is not to find the points of intersection. Because, number one, it's more about the shaded region, the overlapping shaded region, I should say. And number two, technically, the points of intersection aren't even points of intersection, because the dotted line, I can't do this well, because the dotted lines of the green curve are not points that are on this function. Now this is less than or equal to, so I will be shading below this one this time. And that is also within this parabola here, so it's going to look kind of like that-ish on the solid. But the overlapping shaded region is where green and purple are intersecting. So your actual true solution set, we're referring to this area right inside here. This is the solution set right there. That's inside the green and the purple. And it's also what's on the purple that's bounding this overlapping shaded region. So this also counts, anything that's on the purple right there. That's the system for that one. And that is 8b. Okay, let's move forward. Let's go to... I don't know if that's the end of the graphs. So I only use negative b over 2a maybe once. I know that's a lot of people's popular ones. I tend to not do it if I don't have to. Okay, do each operation. Number 9, letter A, 3x minus 2 quantity squared. It's not 3x squared minus 2 squared or 3x squared plus 2 squared. None of that. Leave that out. This is a squared minus 2ab plus b squared. Yes, you could also FOIL it. Here's the concept in play. 3x quantity squared is 9x squared. We're going to double 6x, which is 12x, and then plus 2 is 4. I generally go without writing this in between 1 if you're ever comfortable seeing me do that. But this is a perfect square trinomial. There should be 3 terms. Part B, we have a polynomial minus another polynomial. I can also write this without parentheses. And in writing the second polynomial without parentheses, I'll be distributing that negative. So over here, We'll be subtracting positive 8x cubed, so minus 8x cubed. We'll be subtracting negative 4x, which is plus 4x, and then minus positive 1. And I look to combine like terms. My final result should also be in standard form. Nothing's combining with 3x to the fourth. Nothing's combining with negative 8x cubed, to my knowledge. Nothing seems to be combining with, wow, a lot of things aren't combining. Nothing seems to be combining with negative 8x squared. And then negative 9x plus 4x is negative 5x, and 2 minus 1 is 1. So this is a quartic 5-term polynomial. Quartic as in degree 4, something else that's not on here. This is a quadratic, degree 2, trinomial. This is a quartic guy right here with a leading coefficient of 3. A lot of things we can say on that. Part C, we distribute. I can use that box method if you ever want to, but I'm going to distribute 2x into these 3 terms here. 2x times 3x squared is 6x cubed, not 6x squared. 2x times x is this guy. 2x times negative 9 is this guy. Now negative 5 distributes into these 3 here. Negative 5 times 3x squared. Negative 5 times x. Negative 5 times negative 9. When I combine like terms, nothing merges with the cubic. I got 2x squared minus 15x squared here. Negative 18x minus 5x here, and a plus 45, which does not combine. I have a cubic quadrinomial. Cubic quadrinomial. Part D, there's really no work that needs to be written if you recognize this as a difference of 2 squares here, but the in-between step should be an a squared minus b squared approach. And this is where those show up. Middle terms cancel. Negative 35x plus 35x is 0. Those are gone. You're left with 5x times 5x, or 25x squared. 7 times negative 7, which is negative 49. You get 25x squared minus 49, a difference of 2 squares. Okay. Number 10, parts A through E, factor each polynomial completely. We've done a little bit of factoring so far, none of the bigger boy factoring, but we're trying to find numbers, in this case, that multiply to negative 20 and add to negative 1. If it factors, it'll look like this here. That'll be negative 5 and positive 4. I'm going to leave it be. Not much more to say on that. It's really just it. We're not solving. It's not set equal to 0, nothing like that. On this one, I see a GCF, greatest common factor of 8. And when I factor that out, I got this guy here. If it couldn't factor any further, then we would stop there, but it can. This can factor into x minus 6 times x minus 1. Leave that 8 on the outside. It didn't do anything to you. 9x squared minus 64 looks like a difference of 2 squares. There's a middle missing term. You want to recognize this as, hey, I'm squaring 3x, and hey, I'm squaring 8. It's the difference of those two things being squared. This factors into a minus b times a plus b, 3x minus 8 times 3x plus 8. Remember, the middle terms do indeed cancel, and that's what we get from that. Part D, I'm not sure what the factorization is yet, but I do know that if there's no GCF, and if it does factor, 4x squared comes from 4x times x. It also comes from 2x times 2x. However, 2x's would leave you multiplying 2's by numbers leading to even values, and even plus an even is an even, 19 is an odd. That is not what this would have been. Since I need the 19 to be negative, I need one positive and one negative, and it's likely the negative number will somehow be affected by this 4. 4 times negative 5 gives you negative 20, plus 1 is negative 19. That's the result. 5 are the two factors that I can go here. I know, listen, there's only one problem it looks like we get to factor in this big boy way. I'm not going to spend a lot of time talking about it, but I want to choose factors of 4x squared, boom. Choose factors of 5, or negative 5, boom. And place them in the right spot and figure out when I FOIL this thing out, do I get negative 19x? The answer to this placement is yes. Part E, I have 24x cubed minus 9x squared. I can factor a 3x squared out of here. And inside I'm left with 8x minus 1. And that's it. That's it. All right. Nothing else to factor inside of that one. Oh, not minus 1, minus 3. Excuse me, minus 3. I was thinking of factoring 9 out. That's still it. Okay. Number 11, solve by factoring. So the method will be forced on you. I guess it means to say it is factorable. Now this, I could factor an x out of these two terms, but my goal is to set things equal to 0 and use 0 product property. So I'm going to begin by doing that. Subtract 18 from both sides. There's no GCF, so if factorable, 2x squared comes from some 2x times x. I'm going to see if this has a plus or minus to get a negative 18 factor. 18 can be factored into 18 times 1, 9 times 2, or 6 times 3. I have options. I will not be plugging the 18, the 2, or the 6 into here as to not get an accidental GCF with 2 that didn't exist before. So we'll try some things. Let's try 6 and 3, but I'm going to try 3 here and 6 here. That'll be negative 12 plus 3, which is negative 9. That's not the combination. Let's try 9 and 2, but you got the 2 has to go here. That's negative 4 plus 9, which is 5. Well, I wanted negative 5, so it's not the right number, but it's just the wrong sign. I got to flip-flop these signs, and that's the factorization. 4 minus 9 is negative 5. There it is. Now to solve this, we're going to use zero product property. If this times this equals 0, either this equals 0, so x is negative 2, or this equals 0. When I add 9 to both sides, I then divide by 2 and I get 9 halves. So there are two solutions. Let me squeeze these a little bit more upward this way. Whoa, 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 whoa. Whoa, 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 whoa. There we go. All right. It's number 11a. Number 11b. X squared minus 2x minus 8 equals 7. Once more, if I factored right now, this actually is factorable to x minus 4 times x plus 2. However, if this isn't set equal to 0, you don't go about it with this approach. Do not do that. You can only do this kind of approach if you're set equal to 0. We factor and use zero product property. So we got to subtract 7 over. It's not either x minus 4 equals 0 or x plus 2 equals 0. It's not either x minus 4 equals 7 or x plus 2 equals 7. You have to set it equal to 0 if you're going to use factoring and zero product property. X minus 5 times x plus 3 is the factorization here. If x minus 5 equals 0, then x equals 5. If x plus 3 equals 0, then x equals negative 3. Lastly, part C, 4x squared equals 6x. If you haven't heard it yet, set it equal to 0 before you solve. So subtract 6x from both sides. And this time you're introducing a greatest common factor of 2x. Inside you're left with 2x minus 3, and this is still a product. If 2x times 2x minus 3 equals 0, either 2x equals 0, therefore x equals 0, divided by 2. The 2 can actually be ignored. If 2x minus 3 equals 0, add 3 to both sides, and divide both sides by 2. And this is some solving by factoring. If factorable, it's really the way to go about it. I wish there were some problems here where you get to choose methods to solve and recognize factoring when it comes up. Didn't look like it really showed up here, but we'll move on. But it's a lot of solving quadratics. Now we're going to solve by taking the square root, keep answers as exact values. That means no going to the decimal and rounding final results. Solve by taking the square root, which means until I get this thing by itself and isolated, I'm not going to be taking the square root of both sides. So we'll begin by subtracting 2 from both sides like so. This is where I can take the square root of both sides once I have an isolated quantity like that, and I get x minus 3 equals plus or minus blah, 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 blah. Now the square root of 12 is the square root of 4 times square root of 3, or 2 times the square root of 3. So we're going to get 2 root 3 over here. That's a simplified radical. And I add 3 to both sides. I'm going to get x equals 3 plus or minus 2 times the square root of 3. These are the two exact answers. I could approximate it using a calculator. They don't want us to. But the fact is there are two answers. 3 plus 2 root 3, 3 minus 2 root 3. Part B, same thing. I have something with an x squared. This time it's not a quantity, but just a variable. I have a 9 right there multiplied with it. I do highly, highly, highly recommend that you divide by 9 to begin with. Some people take the square root right now and they forget to take the square root of 9. With that, some forget. There are a lot of things that you mess up with. If you isolate the radical first, it's very hard to make a mistake. If I divide both sides by 9, I'm going to get x squared equals negative 9. And now I can take the square root of both sides from here. And then I get x equals plus or minus, and this is an imaginary solution. I is the square root of negative 1, so I'm factoring this. I'm basically breaking up root 9, negative root 9, into negative root 1 times root 9. Root negative 1 times root 9, which is I times 3, or 3i. This is plus or minus 3i, what we're getting out from there. I, imaginary numbers. Solve by completing the square. We've done some completing the square before, but I don't think we did it to solve. It was we might have used it. I forget. I did a vertex form thing with it once. Completing the square means, I'm going to subtract the 16x over here, and I'm going to subtract the 15 on the other side. My goal in this one, actually this looks factorable, but they said completing the square. My goal here is to find a value that makes a perfect square trinomial on the side to pair and factor it down, but I have to add it to this side of the equation as well. Negative 16 divided by 2 is negative 8, and negative 8 squared is 64. That's the value that makes a perfect square trinomial here in completing that square. This factors to x minus 8 quantity squared, and this here is 49, a perfect square. So now I solve using square roots the rest of the way, taking square roots here. If I'm going too fast, I apologize. This is now end of semester. We should have some of this down. Right? This is not a crash course. Well, it is in a way. A crash course means speed will happen. I got plus or minus 7 being the square root of 49 with regard to solving for x here, because negative 7 squared is also positive 49. We add 8 to both sides. You get 8x equals 8 plus or minus 7. 8 plus 7 is 15, and 8 minus 7 is 1. Like I said, this was factorable. If you get rational solutions, no square roots, that means that this was factorable, but they gave us a method and we're using it, which is fine. It's fine. All right, this next one here, x squared plus 6x plus 16 equals negative 17. Same thing here. If that 16 is not the number that gives you a perfect square trinomial, move it out of the way, subtract it. Negative 17 minus 16 is negative 33. I'm going to add something to both sides, and this value will be 9. The square of half of 6. The square of half of 6. Now this one's not factorable. This part's factorable, but this equation you could not solve by factoring. In fact, it's not real solutions either. Negative 33 plus 9 is negative 24, which means we have imaginary solutions. We only had one of two methods to use to solve. Completing the square or quadratic formula. Quadratic formula comes later. It looks like it comes down below number 15. But here we take the square root of both sides and we get x plus 3 equals. This is going to have an I in the answer, right? Just be ready for that I, square root of a negative. 24's largest perfect square factor is 4. Root 4 times root 6. The square root of 4 is 2, and you get 2y times the square root of 6, plus or minus, baby. Subtract 3 from both sides, you get x equals negative 3 plus or minus 2i root 6. Oh, yeah. Now, they asked us to solve completing the square. That would have been the number one choice for me to use. I would have solved by factoring here, and I wouldn't have used quadratic formula for either. All right, before we do quadratic formula, let's talk about the discriminant, determining number of real solutions in these equations. In order to do it, the discriminant is part of the quadratic formula that is b squared minus 4ac. We are going to do that once we have an equation, quadratic equation, in standard form set equal to 0. I can add 18 to both sides, and I am set equal to 0. However, as much as I want to use this as my a, b, and c, I'd rather use smaller numbers. I can divide everything by 2, and I'm going to. It's not going to change. It'll change the discriminant number. It won't change its sign. If the discriminant was bound to be positive, it'll stay positive. If it was bound to be negative, it'll stay negative. And if it was bound to be 0, it'll stay 0. However, I got smaller numbers to work off of. And I already know this one's going to be 0. I didn't notice it to begin with, but I see a perfect square trinomial. Let's do it. Discriminant is b squared minus 4ac. Negative 6 squared is 36. Minus 4 times 9, 36, which is 0. You get a discriminant of 0. You have one real solution. The reason for this is because you're not adding or subtracting anything in your quadratic formula from your negative b over 2a portion. So your answer is just that single one. This one's already set equal to 0 and already has any GCFs pulled out, so this will probably be a little bit faster. Discriminant here is b squared minus 4ac, which is 36 minus 40, which is negative 4. A negative 4 discriminant means no real solutions, only imaginary solutions. Negative 4 is the part, remember, this is the b squared minus 4ac that goes inside the square root of your quadratic formula. Taking the square root of a negative means means not real numbers, means imaginary numbers. So let's do that. Let's do that kind of stuff in quadratic formula. Let's solve. Full quadratic formula equation. If ax squared plus bx plus c equals 0, quadratic form equation in standard form set equal to 0. Then x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. This is what we're working off of, and I'm going to be applying the discriminant first on my questions. I think it makes this part more streamlined than not. If you've seen my videos before, you probably know what I'm talking about. Let's do 6x squared minus 2x plus 1 equals 0. Add that 1 over. My a is 6, my b is negative 2, my c is 1, not negative 1. Let's begin with the discriminant. We're going to have b squared minus 4ac, which is 4 minus 24, or negative 20. This is no real solutions. That doesn't mean I don't solve. It just means this is the part that goes inside the square root. My answer will have i's in it. So keep in mind, we are going to be doing the square root. I'm going to do as few steps in the quadratic formula as I can. This is 2i root 5. What did we have on that other one before? Oh, 2i root 6. This is 2i root 5. I from the square root of the negative. And 20 is root 4 times root 5. So 2i root 5. So when I do my quadratic formula, it's going to look like this. X equals negative b, opposite of negative 2 is 2, plus or minus, this is the square root of b squared minus 4ac, right? This is b squared minus 4ac, and we simplified its square root. So the square root of b squared minus 4ac all over 2a. 2 times 6 is 12. I'm trying to write as little as possible for the quadratic formula to save myself space and time. Einstein, space-time continuum. All of these can reduce if I divide everything by 2. Dividing these by 2, I get 1, 1, and 6. So this equation in full will now say 1 plus or minus 1i root 5 all over 6. And that's the final answer. And I definitely would have preferred quadratic formula for a problem like that. I'm glad we had that version. All right, letter B. Let's do the same thing. Quadratic formula, set it equal to 0. Now, I have a personal preference of making my a term positive. If you don't, it's whatever. But just believe me, I think it's going to make things a lot easier in life, especially when we shouldn't have a negative in the denominator. So I'm going to make that positive. And that setting it equal to 0 means I'm going to add 3x squared over and subtract 6x over with that positive 4. In one step, I have that. There's no GCF, so I'm going to go straight into my discriminant stuff. Discriminant, I got b squared minus 4ac, which is 36 minus 48, or negative 12. We're really dealing with a lot of imaginaries at this point. Hopefully you're comfortable with that. As far as taking its square root of negative 12 is root 4 times root 3, so it's 2 root 3, but of course there's an I in here. So when we end up simplifying this whole thing, that's what we're going to be writing. So x equals negative b, opposite of negative 6, plus or minus the square root of b squared minus 4ac, all over 2a. 2 times 3 is 6. These can all divide by 2, the same way that I was talking about before. And it'll look like this. So our final solution will be x equals 3 plus or minus 1i root 3 all over 3. No, I cannot work with this root 3 and do some simplification on there. That is not a rational value. I don't know how much more there is. There might be 1 or 2 more pages. Graphing was really the part that made this part a little longer, right? I think it goes to number 20. I think this is the last page. Okay. This is a lot shorter. I was worried this would be a 3-hour thing. So this doesn't cover everything in all the chapters, though, right? I mentioned what wasn't there, and we're going to see some more of what is still here. Do each operation on the complex numbers. Boom, cha-boom, cha-boom, cha-boom. I could FOIL, but this is a difference of two squares thing. These are complex conjugates, a plus b, a minus b. So this is going to be a squared minus b squared. Now, negative 5 squared is 25. However, right here, you got to be careful because 2i squared, quantity squared is 4i squared. But I squared is negative 1. So when I'm subtracting 4i squared, I'm really adding 4. It becomes a real number. This is the whole point of complex conjugates. A minus b, a plus b. It cancels out imaginaries, irrationals, things like that. We get 29. We get 29. Part B, I get to distribute this negative into here, rewrite this without parentheses. This is going to be just like the problems with x's in them, plus I, right? Distribute the negative. Just like x's in them, the two differences are in standard form with real and imaginary numbers, or a complex number standard form, the real number goes first, with the imaginary second. Negative 3 minus 2 is negative 5. 4i plus I is 5i. The other difference is I squared is negative 1. Instead of having x squared and leaving it like x squared and calling it quadratic, I is not a variable. I is a component that makes a number imaginary when multiplied by it. 17 and 18 have some little tricks up their sleeve when it comes to simplifying, and there's more than one way to do them. But the first thing I want to kind of pull out of this thing here is separate these into their own little radicals. Now, as far as simplifying on the top, I can turn this into I root 7, which is as far I can simplify that. And root 12 we saw before was 2 root 3. I'm going to work that out. In some respects, this is almost fully simplified, but I can't yet claim it to be simplified because I need to rationalize the denominator. Top and bottom of this thing needs to multiply by the square root of 3. I could have multiplied by the square root of 12, but it would have left me with bigger numbers to work with, more things to possibly simplify as far as radicals, and also fractions to reduce. You might still have to reduce fractions here, but there's less need and opportunity for it. So root 7 times root 3 is root 21. So on the top, we'll have I root 21, and on the bottom, we're going to have 2 times root 3 times root 3 is 3, or 6. So we'll have I root 21, that's not a 27. We'll have I root 21 all divided by 6. This is the simplified version of what that thing is. Rationalized denominator, imaginary, all that kind of stuff. That's what it is. Part B, simplifying this thing, rationalizing this denominator is the goal. This one is, I'm not going to say harder to do, but this one you cannot rationalize by multiplying by root 2 over root 2 because this has to distribute into here. As much as these two multiplied become 2, then you'd have a 3 root 2, and it's still irrational down there. So instead, the only thing we can multiply by here is its conjugate. We just mentioned conjugates on this problem right here. It creates a difference of 2 squares that effectively cancels out anything that's irrational or imaginary in the denominator. So in the denominator, this is an a plus b times a minus b effort, which factors into a squared, 9, minus b squared, root 2 squared is 2. On top, I get 4 times 3 minus, or plus, or 4 times negative root 2, like that. And 9 minus 2 is 7. So we get 12 minus 4 root 2, all divided. I write before I speak what I'm thinking. All divided by 7. If fraction could reduce, we would, but it can't, so we're going to leave it like that. So the conjugate, 3 plus root 2 multiplied by 3 minus root 2. That's what works this guy out. Once again, that was a squared minus b squared. A plus b, a minus b. That's the goal. Okay, find the zeros, real and imaginary, of the function. This is an instance where I suppose we get to solve using any method. Find the zeros just means you set the y equal to 0 and then you solve. So boom. Now we solve. I'm going to solve using square roots. You have multiple methods to choose. The first thing you could do is divide everything by 5. The only methods I would choose are square roots or quadratic formula. I'm going to go with square roots here. I'm going to just begin by adding the 35 over and then dividing by 5 and then taking the square root of both sides. We get x equals plus or minus the square root of 7. I'd argue that's a lot faster to do than quadratic formula, especially if you don't do the discriminant portion first. That's my belief, at least. All right, we're going to set this one equal to 0 as well. I'm going to multiply everything by negative 1 to get my a positive. This does not look factorable. I want to use quadratic formula this time. I really do. I think that this is going to be the best case to do that with. So my discriminant will be b squared minus 4ac, which is 4 minus 40, or negative 36. The square root of negative 36 is 6i. So when it comes to the formula, x equals negative b, opposite of negative 2. Remember, I'm using this equation. So negative b plus or minus the square root of b squared minus 4ac all over 2a. These can all divide by 2. And I get 1, 3, and 2. And I'm going to now have x equals 1 plus or minus 3i all over 2. I dig it. It's good. All right, solve systems algebraically. We had solved previously by graphing. Now we're going to solve algebraically here. You have two options as far as getting this stuff by itself. I'm going to show you one method one way, one method the other way. One method is by using something called the elimination method, where it's best if you rewrite this and line some things up right here. Your goal is to subtract the result of this thing, meaning like subtract this bottom equation. Turn this y negative, turn this 5x negative, turn this 4 positive, because you can eliminate the y's in the process. Y minus y is 0. And you make an equation when you combine like terms here. You'd have to understand why this is allowed, by the way, in order to really accept it. But you make an equation here with no y's in it. We get to solve for x with that. Okay. So we have an equation here. I don't know if this is factorable. I have no idea. I'm going to give it a shot and talk about that. I can have 9x times x or 3x times 3x. Let's try 9x times x. If a 2 goes, no, 2, no. 3x and 3. Oh, I'm sorry, 2x and 1x. 2 and 1. Still no, but let's try 3x and 3x. 3x and 3x. Now, it doesn't matter where the 2 and 1 go at this point because I just got to switch sides. Negative 3 plus 6 is 3. That does work here. So it is factorable. That's how I'm going to be solving this. And these have rational solutions, but they're fractions. Not as fun. We get to subtract 2 from both sides and divide both sides by 3. And we get negative 2/3. Whoa. And then here we get to add 1 to both sides and divide by 3. And we get 1/3. Now we're not done. We're not done here. Our goal is to find ordered pairs where these intersect. And it's a good thing we didn't solve these ones by graphing, because I don't know where that negative 2/3 and 1/3 would have really popped up. That would have been hard to see. I can choose either equation to substitute in these values and solve for y. In this case here, I'm going to use the bottom equation because it's just linear and one substitution. So I'm going to try 5 times negative 2/3 minus 4, which is negative 10/3 minus 4. Now negative 4 can also be written as negative 12/3, common denominator, which it means I get y equals negative 22/3 from that. So one of my ordered pair solutions here is negative 2/3 comma negative 22/3. Strange numbers, but they are the numbers. The other one I'm going to do by substituting in my other solution is going to be 5 times 1/3 minus 4, or 5/3 minus, once again, the 12/3, or negative 7/3. So this ordered pair is going to be 1/3 comma negative 7/3. And those are the solutions to that system on A, done algebraically. I use the elimination method to get x's to get an equation with only x's in it. Part B, y equals 2x plus 5 and y equals negative 3x squared plus x minus 4. The substitution method could also be used, where I basically take one expression and plug it in for y in the other expression, because this is what y equals. So I can write an equation that says 2x plus 5 equals negative 3x squared plus x minus 4. My goal is just to solve. I'm going to probably set everything equal to 0, add the 3x squared over, subtract the x over, add the 4 over. This sure don't look factorable. I don't even think this has real solutions, so I'm going to go with quadratic formula on this one and solve for the x's, and then plug them in to solve for the y's after. So as far as the discriminant goes, I got b squared minus 4ac, which is 1 minus 108, which is negative 107, which I can all but guarantee is probably a prime number. So as far as the solution bits, these are, I'm going to stop then. We are not dealing with i's in these cases here. We don't deal with the case where this is no real solution, just like when we graph. So here, no real solutions. We're not going to deal in terms of I for that thing right there. That's where we stop, because these don't intersect anywhere, apparently. And I think I believe it. I believe that this graph would have looked 2x plus 5 as something like that. This one would have probably been pretty sharp and gone that way, and they wouldn't have actually quite intersected. I don't know exactly where it would have been, but it would have been something near that. The final problem on this thing, solve 2x squared plus 3x is less than or equal to 2. Okay, let me just rewrite it just so I can see it. Actually, here's what I'm going to first do. I'm going to set this equal to 2 to begin with. What we're going to do is find the critical points of this problem, the values where I can test the left and right of it. I want to find x values that I plug into here eventually that give me a thingy. You'll see what I mean. Actually, let's do this first. Sorry about this. Let's do it like that, but I'm going to then subtract the 2 over and set it less than or equal to 0. Oh, excuse me, I never subtracted 2 over. And set it less than or equal to 0. Now is where I'm going to be doing some critical point testing. I'm going to figure out my critical points by setting it equal to 0. What are the zeros? Because here's the idea of this curve. This parabola somewhere goes positive to negative, things like that. And I want to find these critical points and then find out where I'm basically underneath the x-axis. When am I less than or equal to 0 on what values of x? So here, is it factorable? It looks like it is. Plus 2 minus 1. This would be 4 minus 1, which is 3. It is. This x value will be 1/2, and this x value is negative 2. So these are your 2 critical points. These are not solutions. These are critical points. I could give you the answer straight away from here by knowledge of, again, what this graph looks like as a quadratic equation that goes upward. That means that this graph is doing this at negative 2 and at 1/2. It's crossing downward underneath and kicks back up and does that. So we're trying to find the times when this is less than or equal to 0, like that, when I get negative values. It's less than or equal to 0 between negative 2 and positive 1/2. So I can test numbers. You can plug in a number here, here, and here and plug in and see what you get. Like if I plug in 0, I'm going to use the factored form. I get a negative times a positive, which is a negative number, a negative result. When I plug in something like negative 10, that's a negative times a negative, which is a positive. I get a positive result there. And when I plug in something like 10, I get a positive times a positive, which is a positive here. And I get that result, which seems to match the graph. So it's negative on this interval here, between negative 2 and positive 1/2, and it includes those. So the solutions here are everything x between negative 2 and positive 1/2, and it includes them. These are the ones that make it negative for here, which means it's the ones that make them less than or equal to 2 here. And that's kind of the goal that we got. That's what we had. Okay, guys, and that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I didn't know how long or short this would be. I'm very, I guess, glad that it was short, but I probably spoke pretty fast on that. Not everything was covered, but this was just another nice review to have covered and got pretty comprehensive with. So I hope this was helpful for you. Thank you so much for watching. I have more videos to record to fill out the rest of the big ideas math stuff for chapters 1 through 4, and then I can start to cover some other things later. But guys, that ought to do it. Take care. I will see you in the next one.